Welcome to the deep dive. Our mission today is all about the plumbing, the technological backbone behind modern AI. We're taking a close look at NVIDIA's NeMo and Physics NeMo frameworks,
Right.
and really how companies are moving from these static models to building these dynamic, complex agentic systems.
It's a huge shift. I mean, this isn't just about the initial training of one big model anymore. It's about managing the entire AI agent lifecycle.
The whole thing.
Yeah, from curating enormous data sets to making sure the AI's actions align with, real-world physics and keeping everything safe
Okay,
continuously.
let's unpack that NeMo 2.0.
Yeah,
The source material really focuses on its modularity, right? The whole microservices thing.
it does.
So for a team that's just, struggling with information overload and scaling problems, how does this architecture actually help?
Well, it segments the problem. That's the key. Instead of one single monolithic system that can break, you have these specialized, dedicated components.
And the standout for data handling seems to be NeMo Curator.
It's exactly NeMo Curator. And what's really fascinating here is just the sheer speed. And that's because they made the data pipeline GPU accelerated.
Tell me more about that acceleration, because the numbers in the sources they're just wild,
Oh, they are. You're looking at a 16x speed up for text data.
which is already pretty impressive.
Right, but then you look at video processing, that jumps up to an 89x speed up compared to, the traditional CPU methods.
Wow.
And that's because data processing is almost always the bottleneck. So accelerating that, it just collapses the whole learning cycle.
But that kind of acceleration raises a critical question, doesn't it?
Yeah.
If agents can learn and evolve that quickly,
Uh-huh.
how do you keep them safe? How do you prevent them from going off the rails?
That's where the system really earns its trust. The solution is NeMo guardrails.
So this is like a separate layer sitting on top.
Exactly. It's a programmable layer that enforces safety and topic control outside the foundational model itself.
Yeah.
It's what handles things like prompt injections, the attempts to jailbreak the system.
So it's acting as a real-time policy enforcer.
Precisely. And it's efficient. The sources show it demonstrably increases policy compliance by up to 1.5 times.
Okay, but what's the performance cost?
Crucially, it adds only about half a second of latency. So yeah, it's a small penalty, but it's a necessary trade-off for most applications.
So we've covered the generative side and the safety side. Now, this is where it gets really interesting for me. Physics NeMo.
Right.
It combines AI with physical sciences.
Right.
What fundamental problem is it solving that a, regular correlation-based AI just can't touch?
It's a really deep difference. A regular AI model learns from correlation in data. It sees that A leads to B a million times, so it predicts it.
Okay.
Physics NeMo, on the other hand, learns from causality, from fundamental physical laws. It says A must lead to B because the laws of physics dictate it.
And how is that actually enforced in the math?
Through what they call physics-informed neural networks, or PINs. And this is really ingenious. They incorporate the actual governing physical equation, a partial differential equation, say, directly into the neural network's loss function.
So the physical law is the data.
The physical law is the data, exactly. So the model fundamentally cannot violate the known laws of physics. That's the key difference.
So what does this all mean for real-world impact? We see this in platforms like Earth 2 for climate simulation.
Yeah, this is where we're moving from theory to revolutionary application. Leveraging Physics NeMo, they're using the Cordiff generative AI model to create these high-resolution weather predictions.
And the speed up is?
Up to 500 times faster than the previous simulation methods. That is an enormous leap for understanding extreme weather.
And finally, this all ties back to the overarching goal, right? The data flywheel.
Exactly. The flywheel is that self-reinforcing loop that continually updates, verifies, and deploys the model using feedback.
Using all the parts we've been talking about.
Right. You use Curator to process new data, you use guardrails to monitor the agent's behavior, and that real-world feedback then informs the next training loop. The sources show that by using this system, you can align a smaller model, like a Llama 3.18b,
And get it to perform like a much bigger one.
to achieve performance parity with much larger 7dB models. It's all about making continuous improvement smarter, cheaper, and faster.
So the key takeaway here is that if you want to build truly reliable AI, the infrastructure managing it is where the real leverage is.
Absolutely.
The NeMo ecosystem provides the tools to build systems that are not just intelligent, but also fast, safe, and, well, physically grounded.
And here's a final thought for you to consider. The ultimate goal of all this convergence is what you could call physical AI. These are systems where the LLM doesn't just understand language, but it can accurately predict the physical outcome of its actions in the real world.
Wow.
Think about how many physical processes in our daily life, from logistics and robotics to complex energy management, could be revolutionized by models that simultaneously know language and physics.